Our speaker this evening is Stephanie Moore. I'll let her introduce herself in a moment. Thank you all for coming. And there is a part one of this webinar that you can watch now on our YouTube channel. It's not required viewing for watching this one, but you can, if you haven't seen it, go watch it after this discussion. There will be an opportunity to ask questions, so feel free to either throw your questions in the chat.
We're going to do this live then, so I apologize if my voice gives out at any point. So my name is Stephanie Moore-Lotridge. I am a postdoctoral research fellow in the Department of Orthopedics at Vanderbilt University Medical Center in Nashville, Tennessee. And tonight I'm going to be giving the second half of a webinar entitled The Delight and Villainy of Biomineralization. So as Sam said, the first part of this webinar, that was the delight of biomineralization, was given by my colleague and mentor, Dr. John Schenecker, listed here, and this can be found on the YouTube channel. And tonight we're going to give part two of this, where we're going to really dive into the villainy of biomineralization and how mineralization of soft tissues can be damaging to your body. I want to thank a very critical resource to us, and that is both PXE International and the James PXE Research Fund, which really made a lot of this work that I'm going to be talking to you about tonight possible, and helped fund a mass majority of my dissertation work as well when I was a graduate student. I want to introduce you to our team. This is the Schenecker Lab. I am here in the center. John Schenecker, who gave the first half of this webinar, is here to the left, and the rest of the individuals in this are numerous medical students, graduate students, technicians, research scientists that work on both PXE as well as other conditions of the musculoskeletal system. So broadly, in the Schenecker Lab, we study your muscles in your bones or your musculoskeletal system and your blood. And specifically, we look at how your body following an injury communicates to each other, such that changes in your blood can communicate to the musculoskeletal system and back and forth. And specifically, we're looking at how your body responds to these injuries in order to initiate repair in your muscles and your bones, allowing you to heal fully. So now, the concept of tonight's talk, we're going to be mainly talking about mineralization, and the first half of this webinar focused on biomineralization that was in your bone. Tonight, we're going to talk about it in a different context of mineralization in soft tissue. But I want to start at the very beginning of mineralization. So mineralization is a naturally occurring process. It's defined as the formation of inorganic solid in a naturally occurring substance that has a definite chemical formula with a crystalline structure. Now, mineralization is a process by which our rocky planets, such as our Earth, Moon, and Mars, are formed. And if you remember back to your middle school science classes, you'll learn about mineralization, and that in order to form things like the rocks on our Earth, you require pressure, heat, and lots of time in order to form things such as rocks. Now, ultimately, this natural mineralization process that we attribute in nature is a very inefficient process, taking millions of years to occur at times. And therefore, because us as humans were very impatient, we have developed synthetic mineralization in order to produce man-made materials that allow the construction of great buildings such as the Parthenon, as you see here. This is a replica that's in Nashville, Tennessee, in a decreased amount of time. And ultimately, this synthetic mineralization is a more efficient process. But like natural mineralization in the formation of rocks, synthetic mineralization can also be broken down over time such that it cannot be repaired. Now, fortunately though, for all of us in this room and listening on this web call, mineralization that's occurring in your body, termed biomineralization, is not only timely and efficient, but it also has reparative features that allow it to be healed if you ever hurt it, such as if you broke a bone. Now, biomineralization is utilized by all kingdoms and species, from the formation of shells to the formation of bones that are in your skeleton. For us vertebrates, mineralization in your skeleton is essential to protect your soft tissues, such as your organs, such as your lungs and your heart of your rib cage, but also it provides you the structure to ambulate upright. Without your skeleton, you wouldn't be able to walk and function properly. At the very heart of mineralization, though, is calcium and phosphate, two essential elements that come together to form the main mineral in bone, which is hydroxyapatite. Now, calcium and phosphate circulate at really high concentrations in our blood, such that there's 10,000 times more calcium and phosphate in the plasma than there is in your cells. Now, these concentrations are essential because it gives you really good amounts of calcium phosphate in order to form bones and keep your skeleton strong. But these circulating high levels also means that your skeletal muscles, your tissues, your tendons, all your soft tissues in your body are simultaneously exposed to these near saturating concentrations of calcium and phosphate. Therefore, your body has really important regulation mechanisms in order to promote mineralization where you want it to occur in your skeleton to keep it strong, but simultaneously prevent it from occurring in those adjacent soft tissues, such as your muscle and your tendons and your skin. Now, unfortunately, though, as we age or following an injury, these regulation mechanisms can become broken down. And we see this especially in aging individuals in the form of osteoporosis, where calcium and phosphate are lost from your bone, resulting in a weaker skeleton. But we can also see this dysregulation in the form of soft tissue calcification, especially if we look at your cardiovascular system when cardiovascular calcification happens, or in skeletal muscle calcification. So what you're seeing here is a hip, and all of this here is muscle that has calcified around that hip joint, preventing its motion after a traumatic injury. And these are things that we attribute to things like burn and blast injuries that some of our veterans can withstand during wartime injuries. So knowing that mineralization is a very important thing to be regulated, an important subpoint of this is that underlying all mineralization, whether it's anything in your soft tissues, there's normally an underlying injury component. And we're going to talk about that tonight in context of pseudoxanthoma elasticum. So in the first part of this webinar, we really kind of dove in and focused in how mineralization happens in your skeleton, what are the molecular pathways that help you to form bones. So if you're interested in any of these topics, definitely go back and watch that first YouTube video. Tonight, we're going to build upon that topic, though, and talk about mineralization of soft tissues and how this aberrant process happens and what mechanisms go awry such that the regulation is lost in these. And we're going to tie it all back to pseudoxanthoma elasticum and talk about the regulation mechanisms in PXE that are important for keeping your soft tissues free from mineral. So, as we were just discussing, an important subpoint about soft tissue calcification is that it all underlies injury, and ultimately life is an injury. So every day we get up, we move around, and your body accrues these little tiny micro injuries that are associated with life that over many, many, many years can accrue together in order to drive pathologies we associate with older age, such as osteoporosis and cardiovascular calcification. But it's important to note, though, that traumatic injuries, such as one big burn or blast trauma, such that our war veterans see, can actually model the accumulation of these smaller injuries of life, such that traumatic injuries is essentially just a form of accelerated aging, where you can get calcification of soft tissues in really dynamic measures, as you can see here around the hip. Now, bringing this back to our daily injuries that we accrue every single day, and when we accrue these injuries, your body has specific regulation mechanisms that it uses to combat these little injuries so that once they resolve, you have very little to no injury remaining that can stimulate soft tissue calcification in your body. Now, in the context of pseudoxanthoma elasticum, though, every person sustains these injuries over time, but patients with pseudoxanthoma elasticum have less regulation mechanisms in order to prevent soft tissue calcification. And so when they have little micro injuries of life, there's a little bit of injury left over that can start to stimulate soft tissue calcification. And this happens because your body in circulation is essentially super saturated with these calcium and phosphate concentrations. And this is what can lead to these soft tissue calcifications that you see, such as in the PXE and the skin lesions. So building upon this, I really want to dive into how does your body prevent mineralization from occurring normally, and what's going on in pseudoxanthoma elasticum, and how can we as researchers and as physicians, how are we working on trying to improve this in patients? So great thing for humans is that mineralization in your body is actually prevented in multiple ways, which is great. These multiple ways have backup mechanisms because of how damaging calcification can be in soft tissues, especially in your cardiovascular system. So two ways that we're going to talk about tonight are the protease plasmin. So plasmin is an enzyme that our lab studies extensively, as well as pyrophosphate, and that's going to tie back into the pseudoxanthoma elasticum story. So let's start there tonight with pyrophosphate. So pyrophosphate is an inorganic small molecule that circulates in your blood. Now, pyrophosphate is essentially two phosphate molecules that are connected together by a central oxygen. The pyrophosphate is a really unique molecule because it has these negative oxygens on the outside that allow it to bind calcium in a way that prevents mineralization from occurring. And so if you take calcium out of the mixture, you can no longer form things like calcium crystals or calcium phosphate crystals, as you can see here, such as hydroxyapatite. Now, pyrophosphate has been a long-known anti-mineralization molecule, and there's a really rich history about investigating how pyrophosphate is made and what does it do to our bodies. So looking at how pyrophosphate is made, it first all begins in the liver. Within the liver, and in your liver cells that are known as hepatocytes, there's a transporter known as ABCC6. ABCC6 is essential for transporting ATP from the inside of the cell to the outside of the cell. Now, ATP is the main energy molecule that your cells produce in order to essentially give them life and continue functioning. Once outside the cell, this ATP is broken down into AMP and pyrophosphate, this anti-mineralization molecule we're talking about tonight. Now, as it's broken down, as you can see here from the structure, the AMP can go off and have complete other functions in your body, and the pyrophosphate can then go off and have its anti-mineralization functions. Now, this conversion process of ATP to pyrophosphate and AMP is also happening to a lesser amount inside the cell, following which pyrophosphate can be transported from the inside of the cell to the outside of the cell through another transporter known as ANK. Together, this extracellular concentration of pyrophosphate helps prevent mineralization from occurring in your bodies and in your soft tissues. Now, like all mechanisms in our body, this process is also tightly regulated, such that around your bones, where you want mineralization to be occurring, there's another enzyme known as TNAP, or tissue nonspecific alkaline phosphatase, that actually breaks down this pyrophosphate into inorganic phosphate that, rather than inhibit mineralization, actually promotes mineralization. And this is a really important process in order to keep mineral forming in bone. So in patients with pseudoxanthoma elasticum, they can accrue mutations in ABCC6. Now, when you have a mutation in ABCC6, what this means is that you have a decreased amount of ATP coming out, and therefore a decreased amount in pyrophosphate. And this is a mechanism we hypothesize by which mineralization, ability to prevent that mineralization in soft tissue such as the skin, is inhibited. And so, building upon the pyrophosphate mechanisms, in addition to pyrophosphate being able to inhibit mineralization in your soft tissues, there's another enzyme that I want to talk to you tonight about, and that is plasmin. So to talk about plasmin, I need to take you back in time a little bit to 2015. And this is really where the story of plasmin began in our laboratory and how we started to even realize that it had anti-mineralization functions. So going back to 2015, there was a very talented orthopedic surgeon from Japan that was visiting us named Dr. Masato Uwasa. And during his time in our lab, he was investigating plasmin's role in fracture repair. So now plasmin is an enzyme that you may have never heard of, but is actually really important for our day-to-day life. So plasmin comes from the precursor plasminogen, and plasmin's main goal is that following an injury, your body puts down fibrin in order to stop any bleeding, stop any infection from happening, and kind of seal up that compartment of whatever your injured tissue was. Now, this fibrin, though, has to be removed in order for your body to heal appropriately. And so as your injury resolves and your tissues heal, plasmin is the enzyme that comes in to chew up that fibrin and break it down so that you can heal your tissues appropriately and you don't have clots that can lead to other problems such as a deep vein thrombosis or a stroke. And so plasmin is that essential molecule that's working in both your tissues and in your bloodstream to break down any of that excess fibrin. So in our lab, we study a lot of the musculoskeletal system and including fracture repair. And so we were looking at what plasmin's role was in fracture repair in these studies. And so like any injury, a fracture to a bone is essentially a breach of compartments in which fibrin is going to be laid down at that fracture site. And plasmin, as that bone begins to heal, is going to come in, chew up that fibrin so that it can be removed so that more permanent matrices, such as new bone, can be put down in its place. In these studies we were doing, we wanted to investigate what role did plasmin have in fracture repair, such that if you got rid of it, what would happen to the healing bone? So as you can see here, this is a mouse bone, this is a mouse femur, and with plasmin, the fibrin can be removed, and what you have essentially is a normal looking bone 6 weeks after the fracture. However, without plasmin and without that fibrin removal, what you see is that there's a lot of stuff happening here around the fracture. There's a lot of extra bone, there's screwed up healing, and we really wanted to investigate why this was happening and what actually was going on at that fracture site. If we look more closely, we can do really detailed imaging through CT imaging. So the same type of CT you get in the clinic, we do what's called a micro CT, just meaning it's tinier. And that micro CT allows us to look at tiny mouse bones. And as you can see here, this is a femur. And at that fracture site, it's essentially completely healed. You have bone that goes all the way across the fracture site on both sides. But when plasmin was removed, what we see is a whole bunch of onto that fracture site. What you see is actually you have a bone here and a bone here, but they're never rejoining together, demonstrating that these mice have what we would call a non-union or a non-healing fracture. But what was interesting to us is when we looked into the surrounding tissue around these fractures, we were seeing a bunch of this extra mineralization that we didn't anticipate to see, leading us to ask the question of, is plasmin also a very important protective mechanism for soft tissues from mineralization? And this led us down some further studies. Now, as we were talking about earlier, you have two forms of injury that kind of accrue with your life. You have these little micro injuries of life that you pick up every single day, or you have traumatic injuries. Now, these little micro injuries of life can take many, many years to build up to enough that they can stimulate soft tissue calcification, versus one bigger injury can actually promote soft tissue calcification in a specific tissue. Now, knowing this, we can use this to our advantage in the lab to speed up our experiments so we can look at different pathologies. So what we've done is in mice that didn't have plasmin, instead of waiting for them to accrue these little micro injuries of life, we've instead given them a muscle injury to their calf muscle directly so that we can look at if calcification forms. Using this larger injury model to their muscle, we can then look 7 days post-injury and look for calcification. And what we see is that in mice that have normal plasminogen and normal plasmin activity, you get no calcification. This is the muscle back. This is the muscle back here that we injured. Versus in mice that either have half their amount of plasminogen, as you see here in the middle, or completely missing all of their plasminogen, they have robust soft tissue calcification of that skeletal muscle, demonstrating to us that plasmin is indeed an important regulator of soft tissue calcification, just like pyrophosphate. Now, what was really interesting in this is that if we take that same mouse that had half the amount of plasminogen and instead improve its plasmin activity with a pharmacologic, what you can see is that we can effectively inhibit the calcification forming following that traumatic injury to the mouse's calf muscle. So this shows us that there's essentially two ways that plasmin and pyrophosphate can help prevent mineralization in our body. And so I want to tie this into research that's ongoing right now in the context of pseudoxanthoma elasticum and what we're looking at going forward. So it's been well studied in pseudoxanthoma elasticum that many patients accrue mutations in ABCC6. While the mutations may be different, this is a common feature. Now, one thing we want to look at going forward is, given that many patients with pseudoxanthoma elasticum have a varying phenotype or they have different severities of their disease, are there also mutations in plasmin or the plasmin system that patients may also have that can be dictating how much skin disturbance you have, how much eye, how much gastrointestinal, or how much cardiovascular phenotype do you have as a patient with PXE? Now, from our studies looking at plasmon, we were also able to show in our mouse work that we have therapeutics that we can use to improve plasmon activity. And ongoing with this, we wanted to see also, as a reminder, if we have reduced plasmon here, we can prevent it by enhancing that plasmon activity. But what happens if we take this into a mouse model of pseudoxanthoma elasticum? So just like we have our mouse model of missing plasmon activity, there is also a mouse out there that has that same ABCC6 mutation that allows us to look at pseudoxanthoma-like phenotypes in this animal. And what we see is that in this mouse, if we injure its calf muscle, it also gets soft tissue calcification that we can pick up by micro CT. But what was really exciting for us is that also, if we enhance plasmin activity in these mice, we can also see a reduction in the calcification that's happening. And we want to take this observation into further studies looking at different calcification phenotypes in this PXE mouse that more mimic the skin calcification that happens in patients with PXE, and see if we can use an enhanced plasmon therapy in order to improve these calcification disorders. Now, in addition to these ongoing studies, a lot of work has been looking at how do mutations in ABCC6, how can we pharmacologically, or how can we give a drug that can give back the missing pyrophosphate that is lacking when you have this ABCC6 mutation. And a lot of great work has been done focusing on if you could give back a drug known as a bisphosphonate. Now, bisphosphonates are a readily available drug that is already on the market. And as you can see, their structural similarity to pyrophosphate, the one big difference being this oxygen becomes a carbon in the center, though it's not marked here. And so there's been great studies looking at if we can give a bisphosphonate that also has that same anti-mineralization property back to patients in order to replace that pyrophosphate. Now, also in the last few years, really great studies have been coming out also from groups that are associated with PXE International that are doing research, which is awesome, about just orally giving back pyrophosphate as a way to also improve the lacking pyrophosphate in patients with PXE, and the mouse studies look very promising from that. So with that, I just want to thank all of our labs, and I'd be happy to take any and all questions. Again, really, this work is really made possible by the spectacular funding through the James O'Laughlin PXE Research Fund, as well as the NIH that is supporting a lot of this work, and I'd be happy to take any and all thoughts or questions that you guys may have. Thank you so much.
Great. Thanks, Stephanie, very much. I will open the floor now to questions. You can either type them in the chat, which you can find the chat box on the laptop at the bottom of the screen and on the iPad at the top of the screen. And all of you are muted right now, so you can unmute yourself in order to ask a question. While we're teeing them up, I'll just make a couple of comments. Thanks, Stephanie. That was really nice and clear. I don't know if you came that way to John's lab, but you have the same, we call John the Mr. Rogers of the researchers that we are working with. And so it feels very much like you have the same simple way of explaining things that makes it very, very useful to the people who are trying to understand. So thank you. So a couple comments I'll make around the research is we, again, like Stephanie said, we're very, very grateful to Jim O'Laughlin. He's a guy with PXE. He donated a considerable amount of money to the lab at Vanderbilt so that Stephanie and John could do this research. And without him, we wouldn't be this far. I also want to comment that while we have certainly, as Stephanie said, a number of projects going on looking at a variety of interventions for PXE in humans, none of them are where they need to be at all in terms of being able to tell us whether or not what we're seeing in the mouse will work in the human. And while the mice models are fabulous, we usually have to go maybe sometimes to another animal, to another mammal, and then certainly into human for them. And some of you know that we've been pursuing the pyrophosphate avenue, as Stephanie said. The bisphosphonate one makes us a little worried, and in fact, John has advised us to not be going down that road very far, since bisphosphonates used over a long period can have quite a number of side effects, and they also have a very long half-life. Um, any questions anyone has?
Yeah, and Sharon, I'm happy to talk a little bit more about what our lab's been doing on that bisphosphonate front if you want.
Sure, go ahead with that, and then I have a question from the chat.
Yeah, sure, great. So the bisphosphonate front is a very interesting thing. So like Sharon mentioned, bisphosphonates have been around for nearly 60 years now in clinical use, and they have a variety of different functions. Primarily when we think about bisphosphonates clinically, you've probably heard about them for treating osteoporosis or bone loss. And this is because they have really great function to promote bone formation in our bones and to make them stronger as we age. Now, bisphosphonates are unique, though, in that they have differing functions. Not only can they inhibit mineral, but they can also stabilize mineralization. And one really important concept that we're kind of breaking down in the lab right now is what is the long-term fate of soft tissue calcification in these tissues? What we've been learning from our muscle injury models is that the calcification in that muscle is actually turned over time, such that your body has backup mechanisms to kind of come in and clear out that calcification from your skeletal muscle and able to remove it. And what we're learning is that bisphosphonates can actually get in the way of that cleanup process. And that really leads us to question whether or not those are great therapies for conditions such as D, where we don't know a ton yet about what is the lifespan of that mineral, such as the mineral in your skin. Where does it come from? Is the mineral you are born with, is that the mineral you die with? And those are some things that we really need to start piecing out. And Sharon makes a great point. One of the most important things about bisphosphonates to remember is that there's actually some types of bisphosphonates that can stay in your body for up to 10 years. So we want to be really sure about what these drugs are doing, not only to the calcification, but also to your bone. If you need to heal a bone later on, bisphosphonates can have some problems with fracture healing as well in some different studies. And so we want to be very sure about giving this type of drug and make sure it's really the right drug before we start doing clinical trials and moving forward with it for those reasons.
Great, thanks, Stephanie. So a question from the chat, are there any vitamins such as magnesium that can help to break down mineralization?
Oh, that is a great question. Now, Sharon, I know there's been some work with clinical trials in this realm.
Yep.
Can you comment on that as well?
Sure. Yep. So what we did is we had first done some experimentation with mice, and what we noted is that increased magnesium for mice in their diet appeared to limit their mineralization. When we did a clinical study, and some of you might have been in that, at Mount Sinai Hospital in New York, 44 people, 22 took a placebo, 22 took magnesium. The second year, everybody called a crossover, everybody crossed into taking magnesium. What we discovered in the analysis was that we really couldn't tell if there was any benefit from taking magnesium. And a much larger trial over a longer time with better endpoints would have to be done. That trial cost $500,000, and we haven't been eager to redo it when we have some other things that look much more promising on the horizon. I will say also that one of the very biggest problems in PXE is what's called an endpoint or a biomarker. So in other words, for a drug to be approved in the US and Europe, the Food and Drug Administration, FDA, or the EMA, the European Medicine Agency, needs to know that the drug is effective. And in some conditions, like cancer, they give you the drug and the cancer goes away, and they say that works. In PXE, as you can well imagine, as you've yourself experienced skin lesions, intermittent claudication, angioid streaks and or hemorrhage in your eyes, those things take place over decades. So tens and tens and tens of years in some cases, 30, 40, 50, 60 years. And for us to decide that, for example, we're going to look at the development of angioid streaks in several individuals over time and see whether or not a drug like magnesium or something else actually retards that growth, would take us 20 or 30 years for a clinical trial. Number one, no one will pay for such a long clinical trial. And number two, we need something faster. So what we're doing right now is a biomarker trial. And in the biomarker trial, we're trying to find out, are there other things we can use as surrogate endpoints? So trying to think of a common example of a surrogate endpoint. You might not know if it's going to rain this afternoon, but if the sky is filled with clouds and it got windy suddenly, that's probably a good surrogate for knowing it's going to rain this afternoon. And you don't have to wait all the way to the afternoon. Now, sometimes it doesn't rain too. But in the case of the body, what we're looking for are there various substances in your blood, for example, that are lower than people who don't have PXE, and some intervention might make those rise? Is there something else that we could look at, like something like intermittent claudication, which many of you probably have experienced? When you walk for 7 minutes, 10 minutes, you feel less achy in your legs. If you do that every day, after 3-4 months, you feel less achy in your legs quicker. So that's what you're doing there is your own little clinical trial to show that, hey, if I do this, I'm probably reducing this mineralization that Stephanie talked about. And we now know that's probably because you're actually kicking up your pyrophosphates in your blood. And then we can maybe say, in fact, that might be a good marker, biomarker for the rest of your body. And that if you did that every day, 20 minutes of exercise, let's say, from childhood on, perhaps you'd slow PXE down and you wouldn't lose vision at 40 or 50, you'd lose it at 70 or 80. That's an example, by the way, that there's no concrete evidence of what I just said, but I'm just giving you an example of what we might be able to do with a surrogate biomarker. Stephanie, you want to add to that, particularly about magnesium, since I'm not too familiar with where it fits in the cycle of things that you described for us?
Yeah. So adding a little bit to that, magnesium, like calcium and phosphate, they're ions that are circulating in your body. Um, Magnesium, like calcium, is a positively charged ion. So, a lot of it is just the balance of these minerals that are coming together. And that is one of the reasons magnesium is really great, because it can kind of counteract that calcium and phosphate balance a little bit by giving a different positive ion, is my understanding of it. So yeah, I in total agreement there with everything you've said, Sharon. The mouse studies look super, super promising. And this is one of the reasons, animal studies are very informative for the scientific field. It allows us to ask some of these questions that would be really difficult in clinical trials. But that has to be taken with a grain of salt always, is that a mouse is not a human. There are many things that we can make happen in a mouse that don't happen in human biology, and vice versa. And so there are just important considerations anytime you're looking at literature or looking at scientific studies, to make sure that you're interpreting with a grain of salt and taking things little by little going forward.
All right, I think, Stephanie, looks like you covered the bases. If we get any questions over the next few days, we'll send them to you and get answers for folks. And this has been recorded, so you can listen to it again. It was definitely a good deep dive into this biology that is so important for us to understand. That we're very, very appreciative, Stephanie. Thank you so much.
To any time. So
Great.
good, guys. You guys have a good night.
Yep, you too. Bye-bye.
Stay healthy.
You too.
Thanks, Stephanie.